Fermi level. So it also affects the tunneling current because the tunneling current can be determined by the tunneling between the conduct resonance state and the conduct band state. So it caused the STS measurement with the additional peak nearby the Fermi level. So in our work, we can fit the conduct peak to get the conduct parameter Q, and is the ratio of the tunneling between the conduct resonance state and the conductive band state. So we know that this material have the conduct effects, and we can expect the conductive electron can utilize to interact with the localized spin and to screen or reduce the spin frustration of this condition. So back to the electronic image. You know, in morphology image only show the one-by-one pattern, but in the electronic image, it shows additional pattern, root 3 period, and so we want to know the origin of this electronic pattern. So we change the energy level, because it's the Fourier transfer information, so it's related to the electron band structure. So in this data, you can see the dispersion of the conductive band. And from the STS measurement, we can know the conduct resonance state nearby the Fermi level. So you also can see the root 3 pattern is found on the K point. And it also happened on the cross of these two bands. It means that this electronic pattern can be resolved from the band hybridization between the conductive band and the conduct resonance. So this means that this charge ordering is the charge density wave. So we also to see the phase from the root 3 phase from different energy level. It indeed have the phase inversion, and is the property of the charge density wave. So we already know the origin of the charge ordering. So we also to analyze the conduct Q vector in the real space, we also see the root 3 variation, and it's in phase with the charge density. So we have these two information. So these two information let us to explain how to prevent or reduce the spin frustration in this material. So when the charge reordering on this triangular lattice, we can consider two sides is charge rich and one side is charge poor. And this charge reordering also have the conduct interact with the localized spin, and it will result in the different conduct screen between each localized spin. So it break the equal exchange interaction, and results in the stronger it means the stronger conduct interaction, and means the weaker exchange interaction between localized spin. So finally, we can consider these two spins still anti-ferromagnetic, but this spin already be conduct screen, so it can have the random spin orientation. So in this work, we consider the FE1 configuration, and it results in the spin frustration. And from the real space and case space analyze, we find the condo behavior also have the same electronic period with the charge density wave. Also, they are in phase, so we can utilize this information to explain the new spin ordering in this material. So we also extend this charge distribution into large scale, and it's indeed from the root strip electronic period. So finally, in our lab, from these three materials, these three research demonstrate that we use STM to measure the atomic order of the material, and we reveal the rearrange of the degree of freedom, and this also result in the additional non-trivial property of the material. And this is my report today, and thanks to our corporate group and the PhD and all students in my lab to finish all of this work. Thanks for your attention.
Thanks, Dr. Shi, for your interesting talk. Any question?
Can I know more about the condo configuration?
Okay.
Yeah.
What do you mean?
In one of the slides, you showed us condo configuration there is a strong side and poor side. And what's the discrimination about the strong side and poor side? Is by charge density or by energy experience?
Okay. So from here, and because the condo effect, you can think it's like a screen effect in the magnetic interaction. So if you want to screen the interaction between this localized spin, means if you want to if we want to more weaker between these two spins, it means you need more charge. Okay, so it's why we use this picture. So we have the charge-rich side and the charge-poor side, and also this picture also comes from some theoretical study on the condo effect. So their theoretical results show the condo distribution also induce the charge redistribution of the material.
Thank you. Can I ask a question? So FGT is the
anti-ferroelectric. It's ferromagnetic, but due to its complexity, so you can see it's magnetic curve. And in general, if it's the pure ferromagnetic, the magnetization always increase when you reduce the temperature. So you can see in this picture, you can see up down of the magnetization. And many work show that the effect of the Fe1 atom this Fe1 atom can affect from the different cooling process. Maybe you can find the ordering structure or disordering structure. Also, the APEX results show many different Fermi surface results. So, and it also have many iron atom in the material. So from this theoretical study, you can see many Fe atom have the ferromagnetic interaction, but some, especially for Fe1 atom, they have anti-ferromagnetic to each other. So it means why the diversity magnetic property of this material.
I believe it is an unusual material characteristic. So could you tell us what's the industrial application of this kind of material?
I think basically in this measurement we focus on because it's very interesting that you can reveal the coexistence of the charge ordering and the magnetic ordering, and you doing your study you can know the coupling between these two ordering from the Kondo interaction, and from its application, because basically it's the 2D material, and also have many different ordering in this material. So I think several studies show the Skymian property of this material, but in this study we focus on the atomic structure. So because the study of this material, the Skymian diameter is a little bit larger, so they only explain this the formation of the Skymian is due to the symmetry broken of this structure. But we study in 1 or 2 unit cell, so it cannot direct link to the large scale phenomena in this material. But for large scale measurement, maybe for they also see the strip magnetic pattern, or several interesting magnetic property. So I think you can maybe you can control it very well. So it's very maybe have the diversity for the spintronic application.
Any question? Final question. Can we take out this material from the chamber and expose it to the atmosphere? Is it very easy to be oxidized?
Yes. From the paper research, and the claim is air stable. For STM measurement, we don't understand how stable it is. So first time we clip in the air, and we didn't get very good result. But for this measurement, we clip the sample, we refresh the sample in the vacuum, and we get the good quality of the spectral surface. Yeah. But because it's also several paper also use it to do the spintronic device. I think when they doing the verification process, it's always maybe always under in the air. So they also present a very good transport quality. So maybe different concept on the clean of the surface between different fields.
If there is no other question, then thank you to Dr. Xu Yan.